taught a graduate level educational statistics class at Central Washington University's Masters in Education program. If you've ever taken a class in statistics from a real statistics expert, you may still be dealing with emotional trauma. Lloyd says, in fact, that the word standard deviation is almost like a magical smell. That the smell puts people to sleep. Magical spell. His degrees are in English, so he's not burdened by formal training in statistics, and he learned what he knows about statistical principles by examining real-world situations. That's how he taught his classes, I imagine, which makes them more practical and interesting, like the speeches he gives you here, than what you might otherwise experience from a formal statistics professor. Lloyd will be doing Project 2 in Level 3 of the Presentation Mastery Path. One of 2 elective projects he's chosen from a group of 12. The assignment is to deliver a speech on a topic that's unfamiliar to the majority of the audience. He'll be making many statistical principle of error clear without using any technical terms or mathematical formulas. And in the process, they'll try to clear up some misconceptions held by lots of people about how our elections work. Lloyd Smith, Pennies and Ballots.
Thank you, Mr. Postmaster. Here's a thought experiment for you. You know those big orange Home Depot buckets, those 5-gallon buckets you see over there? Suppose I brought in one of those filled with loose pennies, then dumped them on the table and asked you to count them. How many of you believe you could count them accurately? Right down to the last penny. Nobody? Oh, a taker? Your house on it? Look at it this way. Suppose you counted them twice. Do you think you'd get the same number both times? Don't bet on that either. What that illustrates is a really important concept in statistics called error. Now, in ordinary English, error means a mistake. 2 + 2 = 5. In statistics, that's not true. Error is fuzziness or uncertainty that affects a statistic. It reflects our inability to see the accurate number. Now, that penny thing is a good illustration of that. A 5-gallon bucket of pennies, believe it or not, people have experimented with this. There are between 20 and 30,000 pennies in a 5-gallon bucket of pennies. It depends on how they're poured into the bucket. If you did it perfectly, in other words, made them all flat and filled all the available spaces, there could be as many as 50,000 pennies. Think about counting those and getting it accurate. It cannot be done. I've never tried it. I kind of hope not you to be it, but you can find that out. Now, this concept of error, the fuzziness or uncertainty, what I'd like to talk about is a particular kind of error called the standard error. Standard error is called that not because it's regular or ordinary, but because it's standardized. That is, any circumstance that allows for that error will have it in it. Statistics dates back, like I think right to the 1600s, when probability was first discovered by people who were trying to figure out the odds of various card games in order to make money gambling. And the laws of statistics have been verified over and over and over and over again. Some of them seem unlikely, but that's the way the world is sometimes. Standard error has a textbook definition. It's usually an estimate of a parameter. Parameter is a boundary, a border, like things are within a certain parameter. It's defined as the standard deviation of its sampling distribution. The standard deviation itself is a measure that's used to quantify the amount of variation or dispersion in a set of values. This is the time to nod and be thoughtful, and then just move on. Now, there's a particular kind of standard error that's called the probable error. I love this definition. It defines the half range of an interval about a central point for the distribution, such that half of the values from the distribution will lie within the interval and half outside. The probable error can also be expressed as a multiple of the standard deviation. For a normal distribution, this multiple is 0.6745, an important number. But you probably already knew that definition. This is why I never actually took a statistics class. And you look at that. It appears to be English, but it seems to be an unusual kind of it. Now, the reason that probable error is important is that number, because it defines the range the parameter, the range within which the accurate value of a data point lies. And the narrower that range is, the better off you are, because that means you're more likely to know what the real answer is or what the real statistic is. The wider, the worse. Now, there are lots of things that can contribute to errors, and I'd like to talk about errors in a specific context, and that is our elections. We like to think that after an election, the votes are counted, somebody tells us who won, and that's who won. But that's not necessarily the case, because those election results are statistics, and they are prone to error, just the way every other statistic is too. Now, there is something that does not contribute to error in our elections, and that is voter fraud. It's been experimentally verified that there is no such thing. Now, you've all heard the president claim that there were 3 or 4 million illegal votes cast in the last presidential election, but there have been 25 major legal and academic studies, and they found a total of 31 probable cases of fraudulent voting in the nation. Okay, not 3 or 4 million. The reason a lot of people think there were fraudulent votes cast is that there's a big difference between who is registered to vote and who actually votes. There really are millions of dead people on the voting rolls, but that doesn't matter as long as they don't vote. Their names are on the voting rolls, and eventually they get purged out. There are also people like me who have moved from place to place, and I didn't contact my previous county to tell them I was no longer voting there. I just registered to vote in my new county. And after a certain period of time, I was removed from the rolls in the old one. Pardon me. Anyway, fraud is not a cause of error, but there are 4 or 5 things that really are. One of them is the way ballots are designed. You might remember the presidential election in the year 2000 when Al Gore and George W. Bush were competing against each other. Gore won the popular vote by about 1 million votes, but the Electoral College vote came down to the state of Florida. And in the state of Florida, they have some serious problems with the ballots. They were designed weirdly and caused a tremendous amount of confusion. Nearly 300,000 Florida residents somehow voted for more than one person for president. And that's not a good thing. That's really what the argument that was eventually settled in the Supreme Court was over, what to do with those votes. Another thing that contributes to errors is machine counting. All of you probably got your ballot in the last few days here in Chelan or Douglas County. It's an optically scanned ballot. You black it in a box, and it's fed through a scanner that sees where you mark the box. You may not realize this, but about 3% of the time, those machines will misread the ballots. And often that has to do with the humidity in which the ballots are kept. If they bow a little bit, it might not see them. Hand counting is actually more accurate than machine counting. It produces about 2% error if you have at least 2 people counting. If you only have 1 person counting, the error rate skyrockets because it's such a boring job. You lose your focus. Finally, recounts lead to more error because the more you recount, you multiply the errors from the previous counts is what it amounts to. Now, in a close election, that matters a lot. You remember the election for the governor of the state of Washington in 2004. That was the first time Christine Gregoire and Nino Rossi faced off. That was the closest election for governor in the history of the United States. There were 2.8 million ballots cast, and the final margin after a count, a machine recount, a hand recount, and a lawsuit was 133 votes. Now you might think, okay, Gregoire won by 133 votes. But remember that number, that 0.6745 number? Okay, if you multiply that times the standard deviation of the data set from that election, you produce about 1,200. 131 is less than 1,200. So that means the actual number that came out of that count, that final lawsuit, was smaller than the error. Okay, what that means is that it wouldn't matter. We could still be counting those ballots today. We could have counted them thousands of times. We can never know who actually won that election. Not possible because of that phenomenon of error. Now that's something we don't like to think about. But what it means is that it behooves candidates to run really good campaigns so that they don't end up with those razor-thin margins, because you never know who is going to win when that occurs. By the way, in that penny counting thing, the probable error is 168, so that's the range. If you got within 168, that's the closest you can get under 25,000 pennies at 1.2.